Greetings, this is Artie from Artifact Electronics. So this wasn't going to be a video at first, because last weekend I thought, let's have some fun, take out one of the TRS-80s and write some code for it. This is one I bought a while ago and it worked great, but what I noticed was that the video jittered vertically. So even when the ready prompt came on, it wouldn't sit still. It's like doing this. Well, much less, not that extreme, but it was enough to drive you crazy after 20 seconds or so. So I thought, yeah, let's have a look. The monitor has been tested and it's stable. It was recapped and fixed and whatever a while ago. So it's not the monitor, it's definitely this guy. But as I proceeded to start diagnosing, so let's turn this thing on, give it a little time to warm up, and when I pressed the power switch on the TRS-80, nothing happened. I mean, the dead giveaway was that the red power light didn't come on, but it's completely dead. So I figured let's go and dive in together and see what old age component in this decided to give up. I went ahead and removed there's 6 screws, rather long screws here that hold the whole thing together from underneath. And let's see what awaits us. Let's first take the top off. Very easy. This is, I think, an early revision because it has the Alps keyboard, which is more desirable than the later ones, which were. This has a metal frame. The later ones were mounted on a PCB and were more flimsy and more prone to getting dirty. But this was updated to a level 2. Yeah, notice that it doesn't have the cutout for the numeric keypad, which I guess somebody bought this as a level 1 and then had it upgraded. But I guess they didn't install the keypad or the bezel for, for letting the keypad come through. And but yeah, it's a level 2 and it has the lowercase modification. So these things, yeah, it's put together a bit haphazardly with those plastic and rubber spacers. There's 4 here, and it definitely needs those because otherwise this metal frame of the keyboard will short out things very badly. So let's take these guys off, and then lift out the logic board, and set this aside, and let's turn it over so we can work on it. You might have already noticed that one of the weak links here is this interconnect cable, which after a while seems to disintegrate. I'll show you that in more detail later on. But the first thing to do is to hook up power and have a look at the power supply. The power brick itself has been used previously, was measured, and it is in good working order. Outputs the proper voltages. So it's in here somewhere where bad things are happening. And yeah, let's have a look at the schematics. I think what I'm going to do is the most obvious, and that is test the power supply and see what voltages are getting through and what aren't. Here's a massive main memory array consisting of 16K by 1 DRAMs. And we can already see that 2 were replaced at some point in time. There are Radio Shack service station stickers on this, and I doubt that they installed 2 of one kind, 6 of another kind. So yeah, and these things do die very quickly, so I'm not surprised at that. Power supply is mostly here. Some caps, and let's see what else. This is the lowercase mod over here that's adding a RAM chip and ties into some selection circuitry over here. And the ROMs are mask ROMs that are the latest version, which are level 2 version 1.3. At least that's what it said the last time I ran it. So let's have a look at the schematics. So here's the regulation circuitry, and they took kind of a weird approach because they have AC coming in on these 2 pins, and they also have DC, unregulated DC coming in. Sure, there was a real good reason for that, but the unregulated DC fits this, connects to the upper section. And the upper section generates the 12 volt reference. It uses a 723, an LM723 voltage regulator with a pass transistor, and that generates the 12 volts, which I think are only used for the DRAMs. Keep in mind that, you know, the DRAMs are triple supply, plus 12, plus 5, and minus 5. And but that's not all. Actually, then it uses the output, let's see, it uses the output of the 12 volt as a reference to the 5 volt regulator, and it also uses the negative leg of the rectifier to generate minus 5 volts over here. So let's see how we're doing on voltages. You know, instead of starting out from over here, I'm actually going to go to the output rails and see what's present and what isn't. All right, power is applied over here. I clip the negative lead to the system ground over here. And so the very first thing is, let's check the 12 volt rail, because the 12 volt rail is what provides the reference to the 5 volt regulator. So let's have a look here. R18, which is this guy over here, should carry the 12 volts. So let's turn it on, see if sparks fly. No. And we got 11.9. I mean, this is a small resistor. This is just a current limiter here. So, well, on the regulator side we see 12.04, and on the other side we see 11.9. So it's dropping a little bit across the sky, and it's probably getting, no, it's not getting hot. It probably isn't getting hot because it isn't supplying anything. Actually, it's probably easiest to measure the voltages on one of the DRAMs, because they obviously consume all of the voltages that this power supply generates. So let's see, 12 volts on pin 8. So we'll just pick a pin, any pin, and we see the 11.9 we saw on the power supply. Now, minus 5 is on pin 1. And we got a good minus 5. So finally we go to the 5 volt pin, which is 9. Get my hand out of the way here. And that's about as zero as it can get. So we know that we are missing the 5-volt supply. So I guess we can narrow down things a little bit. So back to the schematics. This is the part that generates the 5 volts. Gets a reference voltage. As I said, the 12 volts coming from the 12-volt regulator up here. But then it has a pass transistor arrangement here. The actual pass transistor is here, and there's a pre-driver for it over here, so to increase the current handling capabilities of this. And the input, let's see. So the way it works is the output of the bridge supplies the pass transistor, but the reference is supplied by the 12-volt regulator. Now we know that the 12-volt regulator is working, so one of the things to test is there any voltage coming in on the emitter of the pass transistor? Now, looking at this, what could go wrong in here? I have seen configurations like this, and for some reason, the majority of problems is, I mean, the gut feel is usually, yeah, the regulator's bad, let's rip it out, put a new one in. But in my experience, what I've seen is, for some reason, the pass transistor itself seems to go bad. And obviously, when that goes bad, it can't pass anything, and this can try regulating all at once, because it has a feedback of the output voltage and tries to get 5 volts to happen, but obviously that is not happening if this doesn't pass anything. So let's have a look at that. But before doing anything further, let's see if the pass transistor is getting something to pass, because if it has nothing to pass, then nothing's going to come out. So R1, yeah, well, you can't see that. So it gets the output, actually from this side, from R1, and then it has 13 volts and change coming in. And that's more than sufficient, to drive the series pass transistor, but there's nothing coming out at the other end. So obviously something in that chain we just looked at is defective. Gut feel says it's probably this transistor. So let's prove me wrong, and let's take it out of circuit. I tried to measure it in circuit, and the readings were completely inconclusive. So I'm gonna take it out of circuit and measure it and see what that tells us. All right, transistor has been removed and hooked up to the whiz-bang tester. Let's see. All right. Yeah, it's pretty funny. I guess so much for my gut feel. The transistor's good. So the next thing to do, I could either go through the remaining 2 transistors in that circuit, or I think I want to replace the regulator, which, yeah, my gut feel says that it's the regulator. So let's see if that's it. Okay, it's the next day. I did some more work, and then I ran out of steam, so here we go. Let's consider on this fun journey. So first I put the transistor back in place. I don't have any video of that because I'm just going to get hate mail from the thermal paste people saying, oh, you put on too much thermal paste, you're going to destroy the PCB. Look, putting on too much thermal paste at worst will hurt your pride, and it's kind of bad form, but it's not going to destroy anything. Anyway, I did this one kind of cleanly. As you can see, there's no large amounts of paste protruding from here. And then, as I threatened last night, I took out the regulator and replaced it, socketed it of course, and it made no difference whatsoever. Still, the 5-volt output is sitting at 0 volts and nothing is working. So, was my second gut feel wrong? Maybe not. But that's going to be hard to prove since the old regulator has all its pins amputated when I removed it, so we're not going to be able to retest this thing. But follow along and we'll see why I am not doubting my second gut feel. I finally went ahead and did the obvious, and that is, well, if a power supply shuts down, it doesn't necessarily mean that it's defective. It may mean that it is protecting itself. So the obvious being, I measured resistance on the 5-volt rail, and I was presented with a dead short. Everywhere, all the chips, everything. So at first, of course, that wasn't very good news, because now I was going to go and have to hunt for whatever was bad on here, which chip was causing it. But that was kind of hard to do because there was no power getting to it to heat up the chip. So I couldn't just touch things or use my non-existent FLIR camera or whatever. So I decided to have another look at the schematic and see if maybe some good fortune was still there. So what I found was there is a Zener diode hanging on the 5-volt output right here. It's a 6.2 volt Zener diode, and I guess it's there to shunt transients down. Transients being if the regulator burps and sends out something more than 6.2 volts, this will shunt it to ground and help protect the rest of the circuitry. And the way this all works is, yeah, just you know how a Zener diode works. When you exceed the Zener voltage, it opens up and all the extra power is diverted to ground. So basically it does very short periods of crowbarring the supply. So let's see what that diode has to say. I removed it from the board, and lo and behold, the short disappeared. So just to make sure here, and the other way around. Wait, didn't I do that before? Doesn't matter. It is in permanent crowbar mode. So what I think happened was and this is why I think my second gut feel was correct, is I think the regulator went out to lunch and started passing the 13 volts that were coming in to the 5-volt output. This tried to do its job, but it's rated at 1 watt. So it didn't take very long for this thing to go bad, going into permanent crowbar mode, where it self-destructed and shunted the entire 5-volt supply to ground. So what I did was I replaced this diode. I didn't have a 1 watt, I put in a half watt, but all that means that if it ever needs to do its job again, it'll blow up quicker than the 1 watt part. So that should work just fine. So let's get set up here and see if we actually fix this thing. But first let's check some voltages. So I am applying power to it now. And apparently nothing is happening because the LED isn't lighting up. And I don't have it hooked up to the monitor yet, but I think I know why this LED isn't coming on. But yeah, let's see. And I'm going to measure voltages on one of the DRAMs. Pin 1 gives us -5. Beautiful. Pin 8. Is that 8 or 7? It is 8. That's 12 volts. And now, pin 9. Oh, look at that. That's the best looking 5 volts I've seen in a long time. And pin 16, which is ground, of course. Showing a little bit of ground resistance there, but I don't think the 2 millivolts is going to create a serious ground loop here. So looks like the voltages are okay. Let's hook it up to the monitor. All right, plugging in the monitor cable. Turning on the monitor. Giving it some time to heat up. And applying power to the TRS-80. Ha! We got a display. Good looking display. But looks like there's a gremlin in there playing with the keyboard. And that's why I early on said I have a pretty good idea what that is, and I'll point you in the general direction. It is the interconnect cable. All the signals come through there, and if anything disconnects or doesn't work properly, you get phantom keystrokes. And I guess the phantom keystroke in this case is a left parent, which the mem size immediately dumps out and starts all over again. So let's have a look at the interconnect cable and basically just do continuity measurements on it and see if anything broke off, because it's beginning to look pretty nasty. The interconnect cable, that is. So it looked like more than half of the traces in this illustrious interconnect cable are broken. No continuity, which would explain why the keyboard was going bananas. And so I took it out and didn't fare too well, plastic melted and everything, but you know, this is unusable anyway. So now the problem is I don't have another one of these, and I'm trying to find the path of least resistance to connect together these 20 pins and not have them break off. I think this was already pretty brittle, but exercising it during the board repair and kept flexing it probably broke a bunch of the connectors on it, or the traces inside. So it's inevitable this part needed to be replaced. So here's my solution. I went through several possibilities. First one was wire from a Cat5 cable. The problem with this is that the copper is solid, and if it flexes at the joints, it'll probably break after a couple of times of taking this apart. So off this went. Next was to use bits of ribbon cable. But I also discarded this idea because the wires are really, really thin. And those probably can't take a lot of stress either, so same problem. These would probably go bad. So I used some crappy speaker wire. I don't know what this is for like a 1-watt speaker or something, but it's still pretty solid. And of course, wire stranded, and it was a pain in the neck to cut all these and solder them in, but they're in. One of the problems with this is that, where is my pointer. The insulation on these isn't exactly Teflon based. So when you solder these things in, the insulation started to melt and expose wire. So what I'm going to have to do, if this works of course, is to give it a nice coating of hot glue, both here and here, to cover the parts of the wire that got exposed, so those don't short. But before all of that, let's have a look. Alright, we're all hooked up. Monitors on. Power and video connected. So here goes. And she's alive. And I guess the primary purpose of this was to fix the vertical jitter on this, which has completely disappeared. The text is rock solid on this now. Oh, and the keys work. So let's do a standard test here. Well, if you don't give it a line number, then it don't do nothing. And yeah, this keyboard is nicer, has a much nicer feel than the later cheapo ones. Or maybe these are, they later on used these. I really don't know when these came into play, but these are nice. So she runs. Also, you can barely see that, but the power light came on. Which, you know, obviously since one of the connections was broken, or several of the connections were broken, it wasn't getting any 5 volts. So the keyboard couldn't really have worked. But yeah, there you have it. I think it's fixed. The original purpose is fixed. And as I was referring to my gut feel earlier on, what I think happened here is that the regulator, the original regulator that was in there, probably had a significant brain fart and started passing 13 volts DC through the series pass transistor, which was caught, of course, by the diode and then died. So my first gut feel was wrong, but my second one was right, because most likely this, the original one, which again I said I can't test it because I have amputated the pins, but I think that guy went bad, and that's what caused the diode, which is hidden between these two, by the way, to crowbar and short the 5 volt supply. So power supply is fixed. By flexing it, we broke the interconnect cables, but that was inevitable. I mean, I'm actually glad we changed these, because sooner or later they would have cracked inside and the keyboard would have started to act up. So what's left is to put it back in its case and see if it still works. Oh yes, and I have to hot glue the connection points over here. Alright, she's all back together, still works. No jitter. No jitter whatsoever. She's solid, so I hope you enjoyed this at least half as much as I didn't. But before we leave, I wanted to talk about a comment I got that left me kind of mystified. The comment was terse, and it basically said you should never use machine pin sockets. No explanation. I disagree with that, and let me tell you why. So on the left is a regular socket, has little springy blades over here that touch the pins on the side when you insert it. And here's a machine socket that doesn't use springy blades but basically has these round machined holes. The advantage of these sockets, or the main advantage of this socket, is that when you insert a chip in here, the sides of the chip basically cut into the machined holes in here, and you get a gas-tight fit between the sides of the pin and the socket. Gas-tight fit means nothing can get in between the pins, and the contact surface is basically sealed. There's no corrosion, and as time goes on, you're not going to have connections go bad, pin to socket connections go bad. Whereas on these, there is no gas-tight connection, and that's why things corrode after a while, because all sorts of things get in between the pin of the IC and the pin of the socket. Now the downside is that after a few insertions, 5 or 6 or so, these holes will no longer provide a gas-tight contact to the pin, because the pin kind of cuts into them, and as the grooves widen, it's no longer gas-tight. But hey, the worst that happens is that if you have a socket like this that has had several insertions and removals, it basically turns into one of these. Oh, and the downside is that these generally cost about twice as much as these. But I still don't understand the concept of why you should never use these. And I welcome your input. So, thanks for watching. Make sure to subscribe and like, and leave me one or more comments. We'll see you next time.